In 1847, a German physicist Kirchoff formulated two fundamental laws. The first law deals with flow of current and is popularly known as Kirchoff's current law, KCL. The second one deals with voltage drop in closed network and is known as Kirchoff's voltage law, KVL. Now, let's concentrate on Kirchoff's current law. It states that algebraic sum of current entering node must be equal to algebraic sum of the current leaving a node. That means summation of incoming current is always equal to summation of outgoing current. That is, summation of all the currents at one node is equal to 0. As shown in diagram, current I1 and I2 are entering at node A, whereas current I3, I4, I5 are the outgoing currents from node A. Assuming that the direction of incoming current to a node to be positive and that of outgoing current to be negative, and applying the KCL, we can write the current equation as I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. Note that the reverse sense of directions can also be taken. Let's consider an example of KCL. Consider a closed network as shown, where supply voltage V is equal to 10 volt, resistance R1 is equal to 5 ohm, R2 is equal to 2 ohm. By applying KCL at node N, incoming current to node N is IT, where outgoing current to node N are I1, I2. By applying KCL, so we can say that total current IT is equal to I1 plus I2. Name it as equation 1, where I1 is equal to V divided by R1. I2 is equal to V divided by R2. So by putting the value in these equations, we can get current across each resistor. I1 is equal to 10 divided by 5 is equal to 2 ampere. I2 is equal to 10 divided by 2 is equal to 5 ampere. So, by putting these values in equation 1, we get total current IT is equal to 7 ampere. Now let's see Kirchoff's voltage law. Kirchoff's voltage law states that the algebraic sum of all the voltages across a closed path is equal to 0. Here, the assumed current I causes a positive voltage drop when flowing from positive to negative potential. By applying KVL to the given circuit, we can write V is equal to IR1 plus IR2 plus IR3, where IR1 is equal to V1, IR2 is equal to V2, IR3 is equal to V3. So we can write V is equal to V1 plus V2 plus V3. Now let's take the example of Kirchoff's voltage law. As shown in diagram, we can apply KVL to ABEF and BCDE. So current flowing in loop ABEF is I1 and loop BCDE is I2. So we can say that current flowing through the junction point BE is I1 minus I2. Now by applying KVL in loop ABEF, we get the equation 20 is equal to, in round brackets, I1 minus I2 multiplied by R1. Thus, in round brackets, I1 minus I2 is equal to 2 ampere. We can write this equation as I2 minus I1 is equal to minus 2, naming the equation as 1. Similarly, we can apply KVL to loop BCDE. So we can get the equation 5I2 plus 20I2 plus 15V plus, in round brackets, I2 minus I1 multiplied by 10 is equal to 0. So naming the equation as 2. By using equation 1 in 2, we can write this equation as 25I2 minus 20 is equal to minus 15, Thus, I2 is equal to minus 0.2 amperes. Let's take a question asked in GATE 2012 examination. The question is, the VI characteristic of diode in circuit given below are I is equal to V minus 0.7 upon 500 when V is greater than or equal to 0.7 volt and 0 ampere when V is less than 0.7. Find the current in the circuit. From the given equation, I is equal to V minus 0.7 upon 500. We can say the diode voltage is equal to 500I plus 0.7. So applying KVL on given circuit, 10 is equal to 1000I plus 500I plus 0.7. I is equal to 6.2 milliamperes. Thus, the answer is option C.